Welcome. Good afternoon, everyone, and welcome to the International Space Sector Interest Network. I'm Martina Blake. I'm the chair of this network and a UK government advisor to the European Space Agency. Today on the screen, you can see I'm joined by Mark Healis from Satellite Applications Catapult, Richard Moissl from head of the Planetary Defence Office at the European Space Agency, and Thomas Ormston, who is the Deputy Spacecraft Operations Manager, also from the European Space Agency. On the agenda today, we have two fascinating presentations. As you can see, we have one from Richard, where we will cover how he and his team keeps us and planet Earth safe from asteroids. And then Tom will share with us how he keeps those spacecraft flying safely in space. In terms of your participation today, please put your questions in the chat and we will pick those up throughout the sessions today. And actually, before we get into the sessions, we will do some brief introductions. And I will first hand over to Mark. Mark, would you like to give us a little update into your role at Catapult and your role within the network?
Fantastic. Yeah, thanks, Martina. And good afternoon, everyone. Welcome along to our latest APM International Space Sector Interest Network webinar. Great to have you all with us this Thursday afternoon. So my name is Mark Healis. I'm the Deputy Lead alongside Martina, working to help grow this network and really shine a spotlight on the role of project practitioners in helping the space sector grow and evolve. I'm a Programme Manager at a company called the Satellite Applications Catapult in the UK. And as a Programme Manager, I'm here to help grow the UK space sector, particularly with a focus on in-orbit activities. So debris removal being one, and in-orbit activity such as manufacturing in space and refueling in space. Hopefully that's a bit of an insight into me, Martina.
Thank you very much, Mark. Richard, if you could give us a little brief introductory about you and your role at ESA, please.
Hello, my name is Richard Moissl, as was mentioned. I'm the ESA Planetary Defense Officer. That means I coordinate and lead the ESA-related contributions to the worldwide planetary defense efforts. Hopefully keeping us safe for the foreseeable and farther future from asteroids.
And then Tom, over to you for your introduction as well, please.
Yes, hi, good afternoon. My name's Thomas Ormston, and indeed I'm the Deputy Spacecraft Operations Manager of the Sentinel-1 mission, which is part of the European Union's Copernicus program of Earth observation spacecraft. I'll tell you a bit more at the start of the talk about my background and things like that, but my job is to keep that satellite safe, and in the past to have kept other satellites safe for the European Space Agency, to make sure they fly from one day to the next. In fact, if I do my job well, then you will never know I'm here, and we will just get wonderful data from space. But I'll tell you a little bit more about what that is when we get to my presentation later.
Great, thank you very much, Tom. Okay, so we will start then with Richard. Over to you to tell us more about your role at ESA.
Excellent. So I'd like to not only keep a planet safe from asteroids, but there's of course one planet which is very special and dear to our hearts. So we of course talk about planet Earth here. But the other thing we need to talk about first is, what are asteroids? So it's star-like bodies in the solar system. They're also called minor bodies because they're far smaller than planets. And we cannot resolve them wherever they are in the solar system. They're really just little dots of lights. This will be more important later. They are everywhere. They are very plenty. There are millions and tens of millions of them all throughout the solar systems. They vastly differ in their physical characteristics, in their size, in their numbers, in their appearance in total. So the only thing they all have in common is that they are on bound orbits around our star, the Sun. So they're all on so-called heliocentric Keplerian orbits, and most of them, they never come near us at all. Here by these small dots. This is not a fancy little animation. It's really a visualization of our database on the left with the red dots. On the right is, this hasn't been translated from German. On the right, there is a little graphic from the JPL colleagues, which shows really nice that they're crisscrossing our orbit all the time. Okay, exactly. So for the sake of not dragging it on too long. So the big question is always what happens if Earth is hit by bodies from space? It's not all Hollywood, and it depends a lot on size. For example, there are trillions of microscopic particles in the solar system, which are called interplanetary dust. And tons and tons of this stuff, up to 100 tons a day, rain into our atmosphere without even noticing it. That's up to millimeter sizes. Once we go to roughly centimeter sizes, we get pretty shooting stars when they enter our atmosphere, but nothing much happens at all. If we go to tens of centimeters, up to a few meters, things become more spectacular. This is the so-called Ribbeck event that happened early in 2024 last year. This one was a little body we saw coming from space and could prepare for it impacting. And you see this is quite a bit more spectacular. Once we go to a few tens of meters, things become quite more dramatic and actually relevant for planetary defense purposes. Here on the right screen, you see an object almost 20 meters in size, and you see that it's really outshining the sun during daylight. This happened 2013 in Chelyabinsk in Russia. And the shock wave from this object burning up in the atmosphere or exploding at the end, the so-called airburst, left more than 1,000 people injured and caused damage in the millions. So from this point, 10 meters diameter and larger, things get serious for people on ground. There's another important, let's say, milestone. When asteroids have a diameter of 50 meters and larger, they will reach the ground in some way, shape, or form and will do a lot of damage. On the left, this array of flattened trees. This is not from an atomic bomb. It's something that happened 1908 over Tunguska in Siberia, where 2,000 square kilometers of forest had been obliterated by an asteroid breaking up. This was probably something we call a rubble pile. That's a very loose configuration of little gravel and small pieces that come in one big lump and then break up. On the right is the Barringer, or so-called meteor crater in Arizona, and this is believed to have been a 50-meter compact iron-rich body that tore a crater of 1.2 kilometers diameter into the Earth. But the effects of this impact, they went also on for thousands of square kilometers. So from about 50 meters diameter, we have to assume that they're capable of destroying the area that a city or urban center would occupy. Of course, there are many different steps in between. Time is too short to go through all of them. The most famous one is indeed a Hollywood-like planet killer or dinosaur killer. There was the so-called Chicxulub event 66 million years ago or 65 million years ago, which ended the reign of the dinosaurs. The good news is about these big ones, we don't need to worry. We know where they are, and we know they will not hit Earth within the next 100 years. But the small ones are of more interest. So we have a space weather program at ESA, of which planetary defense is a part. It includes space weather forecasting. It includes space debris observations and clean space measures, and last but not least, planetary defense. This is the part I'm talking about today. The ESA Planetary Defense Office has as our mission statement the protection of our planet, of humanity and assets in space from dangers originating there. So our tasks are, we're tasked with detecting, knowing where they are, with checking if they're a danger, and with helping or initiating measures to do something against it. If you've seen Don't Look Up, this is a little reference. These people do exist in real life, and this is our logo. We are located at ESRIN in Frascati, at the so-called Near-Earth Object Coordination Center, which can be considered our headquarters, but some small parts of the team are also located in other establishments such as ESOC, ESTEC, and ESAC in Germany, Netherlands, and Spain. respectively. The planetary defense workflow in a nutshell, this is not particular to us. This is how it's done worldwide, for example, also at NASA. You can only first ever react to something you know that exists and you see coming, so to speak. So the first pillar of our activities is the so-called observations pillar, where we detect and track asteroids. The second one is the so-called assessment exercise, or assessment pillar, where we assess the situation, we compute orbits up to 100 years in the future, and we disseminate this information in our information provision activities. Last but not least, if there is something to be done, we are supposed to do everything possible to help mitigating the effects of asteroids. This was it in a nutshell. Now I want to go through a little bit in detail. The observations can be roughly split into two parts. First is the so-called surveys. That's programs that look up the sky regularly to find asteroids. And the second is the so-called follow-up activities. That's where asteroids have been discovered and the knowledge about their orbit is being refined by further observations. The big surveys traditionally are being performed by our colleagues from NASA. Here are two examples, the Pan-STARRS. It's one Pan-STARRS station in Hawaii, or the Catalina Sky Survey in Arizona. These are several stations across the world, and they muster the sky every night, or parts of the sky every night, to find asteroids. We have our own contribution to the international surveys dedicated for finding asteroids underway, the so-called ESA Fly-Eye Telescope network. The first one is under construction right now. Just a little hint is that you don't only need to find an asteroid once in one image to know that it's there and that it's an asteroid, but of course it needs to be observed moving, and so to be able to characterize the movement in these little so-called tracklets. Here on the right is a picture of the very first Fly-Eye telescope being assembled as we speak in Matera in Italy. It will take up duty on Monte Mufara in Sicily quite soon. And to make it short, this one is a unique design or very novel design that is optimized to scanning very wide field of view with a very high resolution. So instead of one camera, it has 16 cameras. The field of view is split over the 16 cameras with this prism that you see in the middle, and this is a bit reminiscent of an insect eye, and therefore hence the nickname Fly Eye for this telescope. And the idea is to get a very high scan rate on the sky, and with a telescope network of 4 telescopes to be able to scan the entire night sky in 2 nights on Earth. Traditionally, ESA has been mostly participating in follow-up activities. We have our own assets. Here are the left and right, the 2 testbed telescopes in Cebreros in Spain and La Silla in Chile, and our 1-meter optical ground station in Spain. But we also have contracts, agreements, and collaborations with observatories across the world in all sizes and shapes. This is a little map of our current network of observations, where we're either having assets or being connected to observational capabilities. And this is really needed for planetary defense. You need to be able to observe all the way around Earth. However, this works only during nighttime. We have a glaringly obvious blind spot during the daylight, something like the Chelyabinsk impactor, which came from the day side, from the inner solar system, so to speak. This could happen any day. NASA and ESA are both seeing this problem, and NASA has just gone through the critical design review of its NEO surveyor mission. That's a mission to the innermost Lagrange point, the so-called L1, observing the inner solar system. And ESA is also preparing a mission, the Near Earth Object Mission in the Infrared, or NEOMIR for short. And from the 2030s on, this one is supposed to be the first ever early warning system, while NEO Surveyor is scanning deep and looking for all the big ones that are missing. Our second main pillar is the so-called assessment. This is separated into orbit determination. So from the observational data, of course, first of all, an orbit needs to be determined and calculated up to 100 years in the future. Then Impact probabilities need to be assessed. That's the impact monitoring exercise. And last but not least, if something is coming straight to Earth, which is the case rarely ever for something big, but mostly for small bits, we also have an imminent impactor warning service. The tools we use for this is meerkats, named after the little cute animals, where always one from the colony is standing guard and checking if anything is approaching that's not wanted by the colony. This one will inform us of imminent impacts within the next 30 to 40 days from discovery of new objects. And our main system is named after the shield of Zeus, Aegis, that is supposed to keep humankind safe from outer influences. This one calculates the orbits for all known near-Earth objects for 100 years into the future, but not only the determined orbits, taking into consideration also all kinds of statistical uncertainties. It does this up to 100,000 times. So this is basically a major a computing system. So what do we do when we find a non-zero impact probability? We publicize this completely open on our risk list on our web portal. Currently, as mentioned, there are about 1,800 objects on there, and this is updated daily and will provide all the necessary information. But not only impacts, we also provide information about close approaches. They happen on a daily basis. As you can see in this example, there are even several close approaches a day. That is quite normal. On top of this, we also provide completely public and free of charge a so-called NEO Toolkit, where we give flyby visualizations. The visualization you saw earlier about the asteroids, this is also free for the public. Observational tools. We even have a very pretty looking synodic optical visualization tool. Don't be fooled by the prettiness. This is a very good diagnostic tool when checking asteroid orbit properties. Can only advertise to go there and have a look for yourself. Last but not least, what do we do if they come? First of all, we want to be right. We don't want to be the fastest in the world. Sometimes we are, sometimes not, but we need to be right. And the best way to be right is not to be alone in this. We have major partners here, for example, NASA, which have the so-called Sentry system. This is their equivalent tool to our Aegis tool. And whenever there is some tools that can be fully pipelined into fully automated warnings, and we're connected, here is an example from Germany, to national assets such as space situational awareness centers or civil protection agencies. In case something is going big, and we just had this for the very first time ever starting of this year, this happened. There are two UN-mandated work groups. The first one is the International Asteroid Warning Network, which is chaired by NASA these days, IAWN or I1 for short. Whenever an asteroid with a diameter of more than 10 meters diameter and a 1% impact chance is discovered, this network will convene, reach 1%, barring the time to completely be certain about this. The second one is the so-called Space Mission Planning Advisory Group. Whenever an object reaches a diameter of about 50 meters and becomes threatening to entire population centers potentially, this group is activated and space-based countermeasures are being studied and proposed. This one is chaired by ESA currently. It has not been activated in the most recent case because it had not been clarified whether the diameter is less or more than 50 meters. Little preview. We just had last night, we had James Webb observations in the mid-infrared, and we will know a lot better about the diameter of this object in the following days and be able to know whether we would have activated the same page had it not dropped with its impact probability to 0 already. Now going further, so what do we do in case an object hits? This is a hypothetical scenario where this object 2024 YR4 would have hit a population center. We are capable of basically providing detailed information to disaster preparedness exercises like here, but I don't want to go into too much detail there. That's the asteroid Dimorphos in autumn of 2022. This is the final 1 hour approach sequence. This was automatically guided, and the task here was for the spacecraft to search for the smaller one autonomously and then guide itself to a planned collision with it. This is sped up. It was 1 image per second, but you can see this went really well. The spacecraft found it, DART, and impacted. And in the last frame, there was no time to transmit all the data. From ground, we saw a spectacular cloud of gravel being ejected from all of this. And this was a lot more than we had expected earlier. From close up, there was a little CubeSat flying along with DART. It was even more spectacular. This big feature here, this is the cloud, this is the main, and the small one is hidden inside a big dust cloud. This experiment went really well, and it was a historic event. We know now that we as humankind have the technology to deflect asteroids, and this one actually went like 3 times as well as I personally would have predicted it. So it was a full success, is almost an understatement. But DART was destroyed as per design during this exercise. It has been followed up by the Hera spacecraft, which will rendezvous with the two-body system early next year and find out what is the asteroid, what does it look like, what did the impact do to it. For example, this impact crater that is shown here in the upper middle, I don't think there will be a classical impact crater. It will have done something different with this very low cohesion object. Hera just recently flew by Mars, so this is not asteroids you see. Well, maybe one asteroid remains to be determined still. This is the Martian moon Deimos flying in front of Mars while Hera is passing by. On the left, where it's seen dark, this is in the optical with the asteroid framing camera on Hera. On the right, where it's glowing bright, is in the infrared. So you see that infrared observations are they have a power that visible observations don't have. So what are our plans for the future? We don't want to stay where we are right now. We want to further close observational gaps, as mentioned, Neomir and other activities. We want to, or we have to upgrade our capabilities because in the future it will be important to keep up the pace at which we're doing this now. And I will show on the next slide why this will come under a lot of pressure. We need to further strengthen international collaboration and networking. And of course, we need to develop, once that we have asteroid reconnaissance and deflection capabilities, we need to make them fast. We need to make them very fast and economically viable so that it's a no-brainer to send a spacecraft to an asteroid on short notice. Discovery statistics, as you can see here, they've gone up almost every year in recent years. Here in 25, we're at the beginning of the year, so it's slowly creeping up. But in the future, we will have the fly-eye scanning the sky faster than any other survey before it. That will have an impact. Then we have the really big gun, the Vera Rubin Observatory, which will look into the sky a lot deeper and also wide and fast. So this one might lead to the discovery statistics exploding upwards. And then we will add the space-based assets on the left. On the lower left, you see Neo Surveyor, a reference sketch on the right, Neomir. All of this will lead to the necessity of getting a lot more computational power behind this and to be able to digest and assess this information much, much faster. Okay, so this has been a bit of a galloping ride through planetary defense. To close this out, I have a little, you might not have heard it, announcement. There will be a completely harmless encounter on Friday, the 13th of April, 2029, when the asteroid Apophis is flying by only about 30,000 kilometers from the Earth's surface. It will be so close that the asteroid can be seen almost with the naked eye, with a pair of binoculars for sure. And when you're in a very dark spot and looking into the right direction with the right, even with the naked eye. This is a wonderful opportunity to learn more about the asteroid, and of course, ESA will not let this pass by, provided we are funded with the so-called Ramses mission. This is a miniaturized, optimized rebuild of Hera. It's a first step towards fast asteroids reconnaissance capabilities. By redoing things, we do it at a smaller price tag, and we do it faster. So very much looking forward to this. I think this will be the astronomy picture of the century when Ramses is taking a picture of an asteroid against the backdrop of Earth. Stay tuned for more there. That's it. Thank you very much. The QR code will lead your smart device with the camera towards our web portal, where there is a plethora of more information available for your, hopefully, information, entertainment, and pleasure. Many thanks.
Firstly, thank you so much, Richard. Really appreciate your insights there. Really fascinating to hear some of the things that the ESA Planetary Defence Office works on, and I'm really keen to promote a bit of discussion. So, if I first of all go to a question from Simon, he points us to a Oumuamua, if I've got that pronounced correctly. He's really tested me there, hasn't he, Simon? Which I believe was Hawaiian for a messenger from afar arriving first in Hawaiian. And this was an interstellar object discovered back in 2017. Simon's question is whether the ESA Planetary Defence Office track other objects like Oumuamua. What's the range of objects that the Defence Office get involved in tracking?
These interplanetary or interstellar objects, actually, they are not part of our mandate. You only see them once when they're passing by. Of course, if one is detected and follow-up is possible, we jump on it and assist. But this is not part of our mandate because when it's not directly on the way to Earth, it will pass by harmlessly and never, ever come back. So the statistics, the chance of an interstellar object hitting Earth is exactly a one-time thing, while the near-Earth objects, they are all on an orbit around the sun. I hope I managed to convey this at least a little bit. They come back and come back and come back, and they cross the orbit of Earth forever, basically, or for almost ever, for a very, very long time. So the chances that a near-Earth asteroid gets to hit Earth, the dice are rolled a couple of times. And this is why they are our primary occupation, because the chance that a near-Earth asteroid is impacting Earth is orders of magnitude higher than anything else.
Great stuff. Thank you, Richard, for the response, and Simon for the question. There's a further question in the chat, and thanks to Adam for this. He asks, are Hera and Ramesses laying the groundwork for mining asteroids?
Interesting question. That depends whether mining asteroids will be a thing today. In a way, for sure, if it comes to pass, because what Planetary Defense wants to know is physical configuration, composition, and everything that is to know physically about the asteroid on top of the trajectory it's on. And that is exactly the kind of questions you would ask if you consider using resources from an asteroid. So yes, asteroid reconnaissance is dual use in the sense of safeguarding against them harming us, and maybe one day being able to use them to our advantage.
Great, thanks, Richard. Really interesting stuff. A further question, this time, I believe, in the chat. So just trying to get to it. So this one, so bear with me. So the account, I think the person goes on to say, your account of the successful defence exercise from 2022 is fascinating. So first of all, I thank you. They go on to say, are there key lessons from that experience that you take into consideration in subsequent programmes? And then just to build on that, also, how do you plan for contingencies in real-time situations like this, where you might not have much time to activate a plan B?
Yeah, exactly. So the lessons learned from Dart are we have the capability, and one lesson is that you really ideally want to know the objects that you're impacting before you're doing that, because we had certain predictions on what will happen once Dart impacts. The vast majority of these predictions didn't coincide with what really happened. So this really emphasizes that the best and most efficient order is reconnaissance first and then deflection. A lesson learned there is, and for many exercises, by the way, we are exercising almost constantly every year. There's international or national exercises. Time is key. Time is of the essence, because deflection is not like a billiard game where you hit it with the impactor and it bounces off at a steep angle or something like this. It's more like this is a mountain. I mean, Dimorphos is a 160-meter diameter body. This is literally a mountain moving through space, and Dart was a Fiat Cinquecento driven into it at crazy speed. So it didn't bounce away. It just, it changed its velocity vector. We used the trick only influencing the orbit of the small one around the bigger one, so it was quite spectacularly visible and measurable. But on an orbit around the sun, there's much more energy to be put into this, and while they move at kilometers or more than 10 kilometers per second in many cases, the vector is influenced by centimeters a second or millimeters a second. So it needs to be done ahead of time quite a bit. So being able to deflect early on is important. And that means that since you cannot reach objects in space all the time, independently of where they are and where Earth is, you have so-called launch windows. The idea is to get our reaction time so fast that we can take the first available launch window. And sometimes it's really hard to do that, because if you have to build a mission, test it, and then find a launch slot, time goes by. In terms of, I think there was this. So what if we do not have enough time? The fallback solution is always, let's say, civil protection. The fallback solution is always trying to find out or doing everything to find out where it hits, what the effects will be, and to prepare for these effects as much as possible so that the damage is limited.
Super. Thanks, Richard. A really detailed response as well, really insightful, really painting a picture of a Fiat Cinquecento colliding with an asteroid. Thanks for that. Really relatable. Okay, well, look, I think what we'll do, we're coming up to halfway through our session today, and perhaps if there's any further questions for Richard, we can either pick them up in the chat, in the Q&A, or indeed we can pick them up at the end after Thomas's session. So, again, thank you, Richard, for what you've shared so far, and hopefully if there's some more questions, we can return to those later. So what I'll do now is we'll pivot to Thomas, and Thomas, right on cue, look at that. Thank you very much for
there I am. Yep.
preempting it. Here you are. Grateful for you joining us today, and we're really excited to hear some of your insights in the world of spacecraft operations. So it looks like you're just getting yourself set up and sharing your screen, which is just coming through, and I can see it wonderfully. So I'll hand over to you at this point.
Marvellous. Then, thank you very much. Thank you, Richard. That's a tough act to follow, but I will try. And I'm going to tell you a few tales from a spacecraft cockpit, what it actually means, what we do at the European Space Operations Centre, where I work for ESA, what it actually means to fly a satellite. My name, as I mentioned earlier, is Thomas Ormston. This is my job. I've been doing it for nearly 20 years now, straight out of university, working at ESOC for ESA in Germany, flying our satellites and keeping them safe, launching them, even killing them on one occasion on purpose, I'll state. Just to give you an idea about my background and my past, I'm from the UK originally, studied at the University of Birmingham. I started at ESA on their graduate trainee scheme back in 2005, and then did the fairly classic career path for people at ESA of working for a contractor company with ESA for several years. And then since 2012, I've been working directly for the agency, flying a whole range of missions in different environments, starting with Mars Express, Europe's first Mars mission, which I looked after for 7 years. It was a fantastic mission, studying the red planet, but also supporting other international projects like the Mars Science Laboratory, Curiosity, and the Phoenix Mars landing. But since 2012, I've moved down, if you like, to Earth, and I've been working on our Earth observation missions with our explorers, Cryosat and EarthCare, which are answering science questions about the planet. And then most recently, since 2020, I've been working on the Sentinel-1 spacecraft. Exactly what the mission is not the focus of my topic today, although these are all fantastic and exciting missions, and I very much encourage you to look at our portfolio of missions. They do incredible things, but I would totally run out of time if I was to talk about what those missions are doing. But instead, I'm going to talk about my job, which is being the bus driver for these missions, not doing the science, not what they produce, but keeping them going from one day to the next. And when people ask what is mission control, or when I ask people what do you think mission control is, what is spacecraft operations, this is usually the image you get, the old classic shots from the Apollo program of people sat in front of computers. We also had a control room right around this same time here in Darmstadt in Germany when we're based. Unfortunately, we didn't really have any screens yet. We just had telephones and some flashing buttons, but we got going pretty quickly. And by the 70s, the haircuts had evolved. We got color photographs, and we got at least a few screens. Moving on towards the 80s, definitely the shirts got louder, the fashion changed again, and then we moved all the way up to where we are today. This is our main control room. It's actually the same room in all the photos, although it's had a few refurbishments since. This is the heart of our center here in Darmstadt. We have many other control rooms. I'll mention a bit about what they do later on, but this is the real core of spacecraft operations, where we perform our most important and most critical activities with the spacecraft, where we do the main job of spacecraft operations. From that room, though, we've had a lot of success. We've had 58 years, in fact, of operating spacecraft, and in total we've operated 94 spacecraft. From that room and other rooms at ESOC, we've flown by asteroids. We've flown out to 800 million kilometers away from Earth, 670 million kilometers away from the Sun. We've controlled 9 ground stations with 900 employees. We've performed planetary flybys. We've landed on solar system bodies. We've orbited planets and comets. We currently have 20, actually this slide says 25 spacecraft currently in orbit. We actually have 24 as of this morning, because sadly it had a wonderful life, but our Gaia science mission finally reached the end of its life today, and we gracefully put it to sleep and switched it off. So this slide is very slightly out of date. But I'm still trying to answer the question of what is spacecraft operations? What is it that I do? Well, most people take a look at it in terms of the ESA project phases. That's one way to look at it. And there's these different phases when you build a space mission with ESA. This is all standardized. And in Europe, generally, you've got your pre-phase A, this first idea of what a mission could be, just a sketch on a napkin. Then you go to your phase A, where you look at the feasibility of whether this mission could actually be done, whether it could work. Phase B is a lot of paperwork, defining what the requirements need to be to actually be able to fly this mission in space. C and D are what most people think of and what a lot of the space industry in Europe is focused on, which is the actual design and development and building spacecraft ready to fly in space. But where we come in is what's called Phase E. This is operations and utilization formally, and this is the point from which the spacecraft leaves the rocket. You see one drifting away there. Then we take over the spacecraft for its whole life, up until and including Phase F, which these days is becoming much more relevant to keep space clean, which is the disposal of the spacecraft at the end of life. So we fit in those red bits, Phase E and F at the end, and because we like to be a little bit self-pitying, We always say the statement that we at operations, and I think this is beyond just the space industry, tend to inherit all of the inadequacies in the design and the previous phases. So if you are involved in spacecraft design, please think of your poor operators having to fly it one day. But what is it I mean by flying? Well, it is pretty much pushing a big red button. That's what everyone says our job is, and it's actually not entirely different to that. However, we have to take account of a few things, and that's what I'm going to go through today. Each mission, each space mission explores a new world. You don't know where you are. You can't see anything. Everything's happening a very long way away. You're alone. Anything can happen. And with all of that being true, you've got to do the right thing at the right time every time. So it makes pushing that big red button quite a bit scarier. It's not scary though, and that's going to be the focus of what I talk about today. I'm going to go through what we do about all these key factors in what makes our job exciting but also challenging. Starting off with the new world. Well, yes, it's true. Our missions do explore new worlds. This could be literally exploring new worlds, like the Hera mission on the right there, which Richard talked about, investigating an asteroid that we've visited, we've impacted, but now it's going to go and do some science there. Or the moons of Jupiter, like the JUICE mission at the top there. But exploring new worlds doesn't just mean going to literal new worlds, but we also have many missions, particularly at ESA, where our focus is on the cutting edge. We have missions like Aeolus, the bottom left there, which was flying around Earth. That's completely normal, but using that big ultraviolet LiDAR on the front of it there to measure upper atmosphere winds from space for the first time. This was complete bleeding edge technology, never before used. And so it was a technological new world, if not a literal new world. But what do we do? I mean, how do we live with living on the absolute cutting edge, bleeding edge? Well, we focus on our history. And that's one of the things you saw it in the slide before of how long we've been operating. We have an amazing history at ESOC, particularly that we can draw on, that we can look back on. We have lessons learned over decades, and we share those across the industry, not just keep them to ourselves. From amazing missions like the huge Earth observation mission ENVISAT there on the top left, the first mission to a comet, Giotto, went to Halley's Comet, and then, of course, the very famous Rosetta mission at the bottom there, which visited and actually stayed with a comet for the first time in history and landed on a comet for the first time in history. And that experience can't drive everything we do, but ultimately that's how we get over the fact that each mission explores a new world. We have real flight experience that gives us a basis to work from. Now, next thing, we don't know where we are. Well, that involves a lot of maths and a lot of whiteboards like this one. We call it flight dynamics, and flight dynamics is what we do to work out where we are. There are two key bits of this. One is attitude. Attitude is what we call which way our spacecraft should be pointed. And I love this photograph to illustrate that. This is the Japanese SLIM moon lander that landed on the moon last year. Unfortunately, as you can see there, it landed exactly 180 degrees the wrong way round, which was quite amusing and actually quite technically challenging to land exactly upside down by mistake. But they still executed the mission. In fact, this is a picture of the lander from a little rover that popped off it and toddled off and took that picture. But knowing which way you're pointed is obviously very, very important in space. This means that our mathematicians, our flight dynamics, need to work with sensors like the pictures there. That big one that looks a bit like an upside down traffic cone is a star tracker. That's one of the ways that we are able to see where we are, by actually navigating by the stars, looking at the stars around the spacecraft and identifying patterns and working out from that how we're pointed. We also use gyroscopes and all sorts of other sensors to tell which way we're pointed. They also then have to turn how we know where we're pointed into how we change or point where we want to. And there we use things like thrusters, small rocket engines, or other technology like the little round metal thing in the picture there. That's a reaction wheel. It's a very fast spinning heavy metal wheel. and of course, if you speed it up, then your spacecraft kicks back in the other direction. If you slow it down, you go in the opposite way. So that gives us a way, without having to burn fuel, to very accurately move and point our spacecraft. But of course, it's quite complicated to operate all of those, which is where all that maths comes in. The other thing is the orbit that we're in, and that is where we are and where we're going. That is already complicated just around Earth. If you look at the trajectory on the screen there, that's the path of JUICE out to Jupiter, doing multiple slingshots through our solar system and deep space maneuvers. This becomes very, very, very complex to plot a path across the solar system to decide where we're going, and also to find out where you are. Around Earth, it's somewhat easier. We can usually use GPS, just like you do here on the surface, but when you're out deep in the solar system, we need to use all sorts of new techniques using our radio signals and things like that to work out where actually in the solar system we are. And of course, we then need to do, again, the maths for how you get there, how you use the rocket engine on the spacecraft, or electric propulsion, which is the very cool blue glow on the left there, how you fire those thrusters, how long you fire them for, what direction, how you use them to put you where you want to be. And of course, some people say, well, we know all this since Kepler. It's a nice, simple circular orbit. The spacecraft just goes round and round. Well, unfortunately, it does get quite a lot more complicated than that, including, which is the equations here, having to deal with even the effects of general relativity. These might seem like theoretical physics theories and things like that to most people, but we need to take that into account along with all sorts of other complicated perturbations and different things. If you don't do that, you don't get to go where you're going. And so that's very, very important for us to do all of that maths and get it right. And I am endlessly grateful to my flight dynamics colleagues, because it means I don't have to do the maths. So that's how we know where we are. But what about the fact that we can't see anything? Now, if you're very lucky, your spacecraft will have a camera on board. I love spacecraft with cameras on board. Usually you don't have that. And so you have to somehow visualize the invisible. And if you look at the complexity of a spacecraft, if you start with a radio-controlled toy at the top there, you've maybe got 10 things you can do to it: go forward, go back, turn left, turn right, brake, and really no parameters, nothing it's telling you. Formula One car, you've got quite a bit more. An aeroplane, you've got quite a lot more things you can ask it to do, and maybe 10,000 or so parameters telling you about its health, about what it's doing. With a spacecraft like JUICE, you've got well over 5,000 commands and over 50,000 parameters telling you every last imaginable thing about the spacecraft. How warm is it? What voltage are things running at? Whether the sensors can see certain things or not? What's all the software doing on board? What does the satellite think it's up to? All of this is streaming down to ground as raw bits and bytes. And so we need to somehow visualize this. Now, it's not important exactly the blobs that are on this graph. Those are the names of different tools we use to visualize it. But what's really important in this graph is that we need our tools to cover this whole area pretty much. And it's these two axes that I've got here. First of all, we need our tools to allow us to see the past, allow us to understand what the spacecraft was doing, whether that's 5 minutes ago, 2 years ago, or whatever else, because that can influence what's happening now and how to interpret it. Then we go through now and we go off to the right there in terms of also modeling what the satellite is going to do in the future. So if we're doing something now, we at least have some understanding of what we've told it to do or what it's likely to be doing in the coming, again, 5 minutes, 1 day, 2 days, 10 days, a month, whatever time horizon we need to get to. And then you've got the vertical axis there, and our displays take us all the way from the big picture, which is very important, nice dashboards, everything is green, everything is red, things like that, going all the way down, drilling down to the bottom there, to the details, the raw zeros and ones that the spacecraft is sending us. And it's important that our systems allow us to fairly seamlessly move anywhere in this two-dimensional space, because sometimes we want that high-level view, but we also always need to be able to drill down in detail. And these are just a few examples of how those displays look. from graphical displays below to the higher level dashboard-like displays. In general, we try and keep the simple stuff. Green is good, yellow is not so good, red is bad. But sometimes our displays fail us and we have to go to, as you see in this photo, slightly more basic methods to be able to understand what's happening. So visualizing and representing is important. And I'm going to take a little aside here to show you what that means, because not being able to see it takes away something that's very natural to us as humans. And that's one of the things I love about spacecraft operations, is that everything is a puzzle. You get limited information and you also have to visualize in your head what's going on. So we had an anomaly on my spacecraft, Sentinel-1A, in August 2016 at 5 in the evening. We suddenly saw several things go wrong. So those star cameras, those star trackers that track the stars, all stopped seeing the stars for about 34 minutes. Then you can see this graph on the right here. Part of our solar power suddenly dropped. We lost 280 watts out of a nominal output of about 3,000 watts on one of the wings of our spacecraft. The same time, you can see these oscillating lines here. This is a sign that the spacecraft suddenly wobbled and then stabilized itself. So we got these unexpected attitude wobbles that we didn't know. And then the next morning, those flight dynamics people, those mathematicians, suddenly said that we appeared to be, they were having problems fitting our orbit. We appeared to be drifting with respect to where we expected to be. So we expected to be on one orbit, and for some reason, we were moving. But we hadn't fired our thrusters or done anything. So some of you, if you're very good, might have an idea of what happened to us on the 23rd of August 2016. We pieced this all together, and we had a pretty good clue of what could have happened. We could only see one real potential cause, and it was a bit scary. Luckily, we do have a camera on Sentinel-1A. This is a picture we took just after launch, looking down our solar array wing. This is the solar array wing that suddenly lost its power on that evening of August 2016. So we turned the camera on and we took another photograph, and to our, well, dismay potentially, we saw that our shiny solar array wing had a 40-centimeter hole in it. That's a big bump. That's actually the exit wound in the solar array after we were hit by a piece of space junk. So we did a lot of research afterwards into what this could have been. We didn't see it coming. It was too small to be tracked by the space debris tracking networks. We know it was likely a human-made piece of debris. It probably weighed about 0.2 grams and was about 1 centimeter across. So that's tiny. It's a bit of foil, 1 centimeter piece of tin foil, potentially. It hit us at 11 kilometers per second. It hit the backside of that solar array that I just showed you, about 45 degrees off perpendicular. And the really scary thing for us was when we did the numbers, we saw that it missed the spacecraft's body, which you can see in the middle there in yellow. It missed that by about 3.5 meters. That means that if this object had hit us 0.3 milliseconds later, it would have gone through the spacecraft body, and that 40-centimeter hole would not just be a relatively harmless hole in our solar array, but it would have completely obliterated the core of the spacecraft, and we would have lost the mission. So we were very, very lucky to have been able to survive that. And in fact, 7 fragments from that impact were then tracked by the Space Debris Tracking Network. So there's 7 bits of our spacecraft out there that are still tracked and still can threaten other spacecraft, which is one of the dangers of space collisions. So it was a scary moment. Luckily, we survived it pretty much unscathed, but it's a good signal for what's out there. And talking about space debris, that could be a whole nother lecture in itself. So we visualize and we represent. Now, next point on here is that everything happens very far away. Well, yes, it does. And the key there is to be able to talk to our spacecraft. That is fundamental to operations. It is the most important thing to us, because if we can't talk to our satellites, we can't control them. We can't troubleshoot and we can't fix things. So we have networks of ground stations, is what we call them, dishes all over the world, starting small, like this one in the Azores. This is about 5 meters, used to track launchers, rockets, as they fly over. up to low Earth orbit stations. These tend to be in polar locations because our low Earth orbit satellites tend to fly polar orbits from the North Pole to the South Pole. So building a station here in Central Europe would not be particularly useful. We would fly over once, and then it would be 24 hours, or actually 12 hours as the Earth turned, before it caught us on the other side. But as the satellites fly pole to pole, if you put your station somewhere nice and snowy, like this one in Kiruna, you can catch those low Earth orbit satellites. Then we have stations pretty much all over the world to contact geostationary orbit. This is where a lot of the communication satellites, weather satellites, television, all those sorts of things are orbiting. They can pretty much see geostationary from anywhere on Earth or anywhere under the satellite's track, so they can be pretty much anywhere. And then finally, you've got the big ones. These are very rare. They're mostly institutional. There's only one commercial deep space station at the moment in Goonhilly in Cornwall. But most are institutional, like this one, which is one of our ESA stations. These are bigger than 20 meters. In fact, our ESA station there is 35 meters across. So that's a fairly sizable building that can move and point at anywhere in the sky. And we have them in a triangle around the Earth. So this is a map of our stations. And you can see we've got one in Malague in Argentina. We've got one in Cebreros in Spain, and we've got one in New Norcia in Australia. That triangle around the Earth means that with those stations, we can see any point in deep space at any point in time from one of those stations. And they're becoming more and more crowded at the moment. We're actually building a new station in New Norcia, and we're looking to build a new station in Malague to really boost that, because this is becoming more and more in demand for missions going out into the solar system, missions going to the moon, missions going to the Lagrange points. But on top of that, you see we have dishes all over the planet that we use to keep in touch with our spacecraft, and that's super important. And what's also important is you see the blue ones are actually our stations, our ESA stations, but we work a lot with commercial partners, the orange stations on there, and also with the green stations, which are institutional partners from space agencies around the world. And we all have standards. They're made up by agencies like CCSDS and ECSS, long, complicated, and mouthful acronyms, but super important to have that standardization so that every agency can interoperate. And that good ground segment is basically how we deal with the fact that everything is far away, because we can still get in touch with it. So, anything can happen? Yes, it can, and we're up to another graph here with its with two axes on it, and one of the words is trying to come off the edge there, complex. But basically here, this is splitting up what we do, and we do have to deal with the fact that different activities in our day-to-day work, whether it's producing data, just normal babysitting of the spacecraft, or the very intense operations, what we call LEOP, launch and early operations phase, they are very different in terms of how you operate and how you plan for what you're doing. They go from, on the left side, things that are very unique. They only happen once in the mission, to things that are very repetitive. They happen every single day. And then on the vertical axis there, you've got those things that can be complex, or they can be very simple. So down in the bottom right, you've got a routine pass. We do 3 passes on my spacecraft every single day. They're super simple. They happen every day. Very easy. Of course, we still need to know how to do them. Up to the top left of that graph, indeed, something like launch and early operations, the most critical part of a spacecraft's life. That's hugely complex. You only do it once. It's a real make or break moment. But everything on here is regulated by piles and piles of procedures. You can see some of them there. That is a tiny snapshot of just a few pages of the hundreds or probably even thousands of pages of procedures that any mission will have. And this is key to how we manage all of these phases, how we somewhat manage the chaos, is that we have procedures that deal with everything we do. Everything that we do on the satellite, we write down how we're going to do it. We check things, we do things, we check them again. We write it down, not quite for dummies, but almost. And critical in there is not just the things that should happen. We don't just write those down, but we also spend a lot of our time dreaming up nightmare scenarios of things that could go wrong, and writing what we call contingency procedures, saying, look, if this goes wrong, if that goes wrong, what would we do? How would we handle it? And then we practice that on simulators. We do it while things are calm, while nothing's going wrong, because that means we've got a nice, reliable template so that when everything does go wrong at 3 a.m. on a Saturday morning, you can come into work, pull out the procedure, and not have to invent things, because one of the key lessons we have to learn when we're learning operations is to think quickly, or to think off the cuff is to think wrongly. There's almost always more time than you think, and the best thing we can do is to take a breath, find the right procedure, trust in the people that wrote that procedure and tested it, and then execute it step by step. And that is what ultimately brings order to that chaos. That anything can happen, is to make sure that we prepare for nominal situations, contingency situations, for everything. And then finishing up, we're alone. Well, yes, we are. There's no one else coming to save us. But you've already seen a picture of this room, and this is not alone. You can see lots of people in this room. This is actually during a critical phase where we've got all the different people, and they're all there to do different jobs to make sure that this mission works, that whatever activity we're doing works. In the front row, you have my job, Spacecraft Operations Manager. I'm in charge of those front rows that are dealing with the satellite. Next to them sits a spacecraft controller. They're actually the only person in the room that can talk to the spacecraft, that can tell it to do something. But they're not allowed to tell it to do anything without being instructed to. This is to form a sort of layer of separation to make sure that there are at least two pairs of eyes on everything we send to it. So if I tell the Spacon send this command, they can tell me, Tom, that sounds crazy. And either I say, oh my goodness, yes, I'm sorry, or they say, or I say, look, do it anyway, in which case they will write down, Tom told me to send this command. It sounds a bit childish, it sounds a bit finger pointing, but actually it's quite the opposite. We're in the business of managing and mitigating human error, not in eliminating it. Humans will make mistakes, that's part of being human. Our job is to make sure that those mistakes don't have any impact. And things like that allow us to trace back why something was done, even if it was wrong, because that's very important in troubleshooting. And one of the things we learn when we work in this room is that similarly, blame and shame are things that we have to leave at the door. I wish I could be that zen in day-to-day life. I'm not, unfortunately. But when we're in this room, we have to know that blaming people, telling someone, oh my gosh, how could you make that mistake? That's so stupid of you. That doesn't help, because it leads to shame. And if you're ashamed of something that you've done wrong, that means that you are potentially going to hide a mistake that you've made, and that can cause that mistake to snowball and get out of control. The best thing for us in this room is to be able to put up our hand and say, yep, I messed that one up, and everyone just say, okay, we understand, let's look at why it happened, because it's almost always a reason why it happened. It's very rarely that we have people that just mess up for no reason. Maybe someone was overloaded, maybe the procedure wasn't clear. Let's look at how we can stop it happening in the future and how we can fix it. And we have an amazing team helping us do that. Around the front row there, you've got the different subsystems. So I say I'm the one that's coordinating all of this, but each position is then somebody looking at a very specific part of the satellite. They're really drilling down deep into their bit of the satellite, and my job is to bring all of those great experts together as a team. Then on the back row, you've got people taking care of everything that's happening on ground. So on the front row, all we have to worry about is the satellite. So you have a ground operations manager, but also behind there, you've got computers, IT support effectively. You've got our network, ESTRAC, that's managing all of those ground stations I showed you, basically doing everything on ground, whether it's our software, whether it's those dishes, to make sure that we have seamless communications with the satellite. Of course, software support is important. That our IT support, we have project support. These are the people that actually built the spacecraft and worked on it all the way through. They're there partly because we need their expertise. They know everything about it, but also because if we need to make difficult decisions in the moment, we can ask them. We have another room with those wonderful mathematicians, our flight dynamics people. We, of course, have our flight director, the person that's in charge of everything that's happening in the room there. He or she is who brings this whole thing together. And very importantly, we have down in the basement a simulation studio. When we do work in this room, we work usually 12 hours on, 12 hours off, so 2 shifts. But we don't come into here on launch day for the very first time. For 2 to 3 months before we actually do anything in this room, we will do a series of what we call simulations, where we will come here and those people down in the basement will pipe things up to our screens to make it look like we're flying the real thing. To us, it will feel real. We'll be talking on our headsets. We will be doing everything like it was real. That starts off normally, and then those horrible monsters down in that basement studio will start injecting failures for us. They will break the spacecraft, the simulated spacecraft, and we'll have to practice how to fix it. But not just that, they'll do other things. They will put a fake bomb in the room, and we'll have to remember our evacuation procedures. They will fail consoles. They will call you up and say, especially if you're the real super hotshot in the room, the one that knows everything, the go-to person, they will call that person up and say, you had the chicken for lunch, it was bad, you're sick, leave the room. And they just have to walk out, and we have to do without them. They will play radio over our headsets so we can't hear each other. They will look at things that we are doing, and they will expose those problems to us. Once we were loading all of our procedures on our laptops over Wi-Fi, so they killed the Wi-Fi router, and we didn't have backup copies. They will expose any weakness in the team. And it sounds horrible, and we do sometimes really hate them, but ultimately you learn nothing as well as you learn it when you're actually living it. And that simulations campaign is what takes us from just being people sitting in front of computers to a real cohesive team that can really handle anything. And we've saved many missions over the years by that team effort. And I'm going to finish up now with showing you some family pictures of what exactly that looks like. And this is Sentinel-1C. This is one of my spacecraft. And this we launched actually just in December last year. So it's very fresh in my mind. And it's a fantastic spacecraft. It was a lovely launch. It also didn't go according to plan. This is our rocket. On the day of the launch, or the planned day of the launch, you can see that platform that's in front of it. Yeah, that's stuck. Unfortunately, we had to delay our launch, not because of any fancy technical issue or complicated space thing, but because that gantry couldn't be wound out of the way. The hinges were stuck. We spent quite a long time in the control room staring at the gantry and sending each other pictures, but unfortunately it didn't budge that day, and so we had to go back to the drawing board. We literally do have a drawing board in the room. Actually being able to scribble things on a whiteboard in a contingency situation is very, very important to us, but we had to have a meeting, look what was going to happen next, and work out that okay, we would go for launch the next day. We baked a cake for the next day because we realized that we'd not been paying good enough attention to our superstitions. And yes, we are quite superstitious despite being technical, and having good cakes is an important way to bring luck before a launch. We also had the tradition of every team that's flying a mission here at ESOC puts pictures and nice little good luck cards on the door of the control room to give us a boost as we go into fly. And you can see me very excited there. The next day, the rocket did come out of its building much more smoothly than before, and very quickly we were turning our faces from looking slightly concerned to looking much happier as the spacecraft launched into space. And it was actually a fantastic LEOP period, nowhere near as scary as all our simulations, which is exactly how we like it. And we even had time to make some memes as we went, because we could really enjoy ourselves. We did get to go off and have a break. Sometimes we let the junior members of the team take care of the spacecraft. But ultimately, it was smiles all around. And this is what I say. When I say we're not alone, we're really not alone. It may be that no one from outside is coming to help us, but our team is absolutely fantastic. And that really is the main thing for me, aside from everything else I've mentioned. So, at the end now, you must do the right thing at the right time always. Another way of saying that is the famous quote. You can see it at the top of the screen there. Failure is not an option, from one of the most famous operators, Gene Kranz. Yes, he is right. Failure is not an option for us. And if we apply our procedures, our planning, and our training always, then it will work. Although we love Gene Kranz, we sometimes, though, prefer to take what's called the astronaut's prayer from Alan Shepard, the first American in space, which is at the top there. Don't make me read it out, but it possibly more accurately sums up sometimes how we feel sitting in that room, being in charge of millions of euros of spacecraft, but I wouldn't change it for the world. I absolutely love it. So thank you very much. If there's time for any questions, I'd be happy to answer them.
Thank you very much, Tom. Fascinating. And we do have several questions in the chat. We have around 10 minutes or so left. So I will read out some of the questions. So the first one, we have here from Adam. So you talked earlier about the kind of the maths and flight dynamics. So are there any open tools for calculating flight dynamics in real time? So I believe Adam is building a flight operating system himself, and would like to know how
Excellent.
he could use those in his software.
Yes.
And then also, in kind of the sort of the standard software that are used at ESA as well. So.
Yeah, absolutely. And there's actually a platform called Space Codev. I can maybe put it in the chat there. This is where we share software, share European software, particularly ESA software. And one of the projects on there is a project called Godot. Godot is our flight dynamics toolkit that we use at ESOC. And it is, completely open and free to download and use. It's a very modular system, so that was the whole aim of the Godot system, was that you can take bits of our flight dynamics system, you can take all of it, build a whole flight dynamics system from it, or you can cherry pick parts of it, modules of it, to do certain aspects of the flight dynamics job. So that's definitely something that's getting a lot of traction at the moment. It's relatively new. It's a year or two old since we launched it, but it's a really nice way to take advantage of all that experience and all of our flight dynamics knowledge and software and use it in your own projects.
Thank you, Tom. And as a follow-on question he's asked is, how much work do you find yourself actually doing at the terminal?
At terminals, well, more than I would like. So, I mean, that comes back to those displays. Actually, we try and arrange our jobs so most of the time we have to do as little as possible. That's not just because we're lazy, we try and be efficient and things like that, but a lot of our job involves getting involved when things don't go according to plan, because indeed when you've got everything automatic, that's great, but sometimes it breaks. And so, yes, more often than not, we will have to go into the terminal or drill down into bit streams and byte streams from the spacecraft and try and work out in a strange situation what exactly is going on, and so that's when we tend to get deep down into the guts of our systems and have to work out how to fix them.
Thanks, Tom. And we have a question from Joshua. So he says, thank you for such a fun presentation. ESA have a fantastic record, which we do, yes, and long may that continue. But with the private push into the industry, do you see any changes with regards to the kind of the lengthy procedures and standards that we use in the space sector? Do you kind of see that changing at all?
Yes, I think I do see it changing, because there's our way of doing things, and what I didn't say is everything is a trade-off in space and in operations particularly as well. How we do operations fits very well the sort of missions we fly. It would not necessarily fit well a startup trying to be very lightweight, very agile, and I think there's a place for both of those. They all have use cases depending on what you're trying to achieve. The standards, indeed, I think it's a very current topic at the moment, is how we adapt our standards, which are typically, yes, very heavyweight, very involved and things like that. But there's a trend to say, well, because they're so heavyweight, we throw them away. And that's a trend that I think both sides need to take account of. On the side of the people that want to throw those standards away, we need to say that, well, there are lessons in there that can be captured, and there are great things that it enables. Interoperability, it helps keep the experience from space flight over many, many years. But there's definitely work on the side of people like us that develop standards to look at how we can adapt those and modernize them to be more lightweight, to fit these new use cases. Because I think ultimately obeying those or following standards opens up a lot more doors, particularly with respect to scalability as those startups grow and things. So they are important, but yeah, fully open and honest to say in the present state they are somewhat too old-fashioned, somewhat too heavyweight, and need to evolve.
And how many years would you say, Tom, that it takes to, let's say, get up to speed with the standards and the procedures that you have to operate in your role?
As they are at the moment, quite a long time. Yeah, I mean they're quite dense, quite hard to read through. But actually, I mean they're all publicly available, and actually to get the first idea of what they're looking at is not actually that tricky. And I would advise anyone that's getting started with building a ground segment, building a spacecraft. They look horribly scary and they are terribly boring to read. But they're not actually that difficult. It doesn't take that long to at least get to grips with the basics. Whether you apply them fully or not, that's again a trade-off. But they're not actually that hard to get into.
Yeah, thank you, Tom. And I know we have a couple of questions around sort of careers. I have posted in the chat the ESA careers website, so please do take a look at that. We do host these webinars quite regularly, so I would kind of look on our network page through APM, because there will be future ones around careers in the space sector as well. So for anybody that is interested in careers in the space sector or ESA, do keep an eye out for future events. So I think that is all of the questions that we had in the chat. The only thing I was going to just check with you on, Tom, is so we have our biomass launch coming up at the end of April. I will post that in the chat because there's some information on there. Could you give us a little sort of brief overview of that? And I'm sure you've got a starring role at ESA Live TV that you might want to share.
Indeed, yes. I meant to mention that during my presentation. Yes, I am, luckily or unluckily, I would love to be flying it. It's a really fancy mission. It's going to have this huge mesh sort of umbrella-like reflector that will deploy. So it's a very exciting mission from our Earth Explorer series. Yeah, launching on the 29th of April. Yeah, I would love to be flying it, but I'm not. I'm busy with Sentinel-1. But I will take some time out, and indeed you will see me probably in this room behind me doing some segments during the live broadcast for the launch of Biomass. So if you want to hear me again taking you around the control room and showing you what we do at ESOC, particularly during that intense launch phase, then you can catch me there, and it's well worth tuning in and watching that launch.
Great, thank you, Tom. So I have posted in the chat there the link to the Biomass mission and also a link to ESA TV, where you can watch that live and see Tom in action in the control room. So we are a couple of minutes till the end. So first of all, I just want to say thank you both very much for coming along today. It's been fascinating hearing about your roles in ESA and, you know, keeping us and planet Earth safe, keeping all these spacecraft flying safely in the universe. So thank you both very much for coming along to talk to us today. I know Mark has put in the chat as well about our future events and a little bit more about how you can also join the International Space Sector Network. If we don't have any further questions, which I can't see anything else. Oh, we have one very quick one from Adam. Okay, he's just asking what embedded systems do we use, because NASA have F prime and CFS.
Oof, yes, I wouldn't be confident answering it completely. I mean, obviously, on the ground where we are, we're not so much using embedded systems. We tend to be using software platforms and things. Of course, our spacecraft do have plenty of embedded systems on board. I would horribly pass the buck to our website and things like that to look for more information on that, because I'm afraid I'm not so aware of that.
That's fine. Thank you so much, Tom. Okay, so I think we will wrap up there. There are no more questions in the chat. So thank you both today. So we will end there and we will see you all in May, 8th of May.
Thank you, everyone.
Great. Thank you, everyone. Take care.
Bye-bye.